Hello, this is Jeffrey Fox, and I'm talking about the perspectives on high performance computing in the big data world given at HPTC 2019. This is the last part of this presentation, and this is the long version of the presentation. But even if it's long or last part, the conclusion is that HPC's got really promising. And there's some incredibly interesting new things that need to be investigated, particularly focused on what I call machine learning around HPC, where it looks as though we can not do both evolutionary and totally transformative results, which we really have to focus on, in my opinion, because I think if we do that, we will really make HPC a dominant force in the world. Thank you very much for listening to these lectures, and please, this last section is not so long and is full of possibly, hopefully interesting general remarks. Thank you. So this section has two components. Dominantly is the actual computer science issues, challenges and opportunities, both software and hardware. All right, computer science issues. Well, as far as I can see, there are lots and lots of questions because little has been studied. There have been several actually very promising results, but they haven't been done so much from a computer science point of view, looking at what things depend on and what are the real issues. So we don't know what computations can be assisted by what machine learning, and in maybe there are 9 scenarios as I gave or less. Maybe some of them are not really important that we should focus down or focus up. What is the performance, both in computer time and capability of the different choices for deep learning or machine learning? And as we're going to get to zettascale computing, what do we do with it? People are thinking about exascale, but you can get zettascale. We have to look at all these algorithms, see how they can be machine learning assisted, and we need to understand how we implement this dynamic interplay between the data and the control of who's in charge of what, and between the simulations of the machine learning, which are, I think will be necessary in the more sophisticated versions of this work. I've already pointed out the important analogies between time series and simulations, because they're 4-dimensional time series. Maybe there's some nifty analogs between the industry problems and the simulation problems. That would be fun. So we've already said there's been little study of the best neural network structure, especially for these hard problems like predict fields from fields and the data assimilation. We don't really know how big the data set is. It just seems to be quite small at the moment. And whether that's just an accident of the toy examples we're doing now or really will continue is not clear. I'm a little surprised people aren't just going in there and getting exascale and zettascale. I think that's what I would be doing if I was on one of those large NSF or DOE machines. There's lots of interesting parallel computing issues, because if you think about these parallel problems, and we do these learning surrogates, we might find out that while we're running, we have to actually not just we can't use the surrogate. We have to calculate it from scratch, because we're going to presumably learn not just the value but the error, and then we plug in a surrogate parameters, and we find the error is huge, so we have to calculate it. Well, that's going to produce all sorts of interesting challenges for parallel computing. Exciting. And as I said, we really need to understand errors better, because we shouldn't be predicting just values. We should predict errors. The results I showed you found errors by comparing the results with the simulations, but we need to predict errors and learn the errors, so that, because when we are doing these surrogates, we need to make certain that we actually can get reliable answers. Well, we need to know if you can actually find errors. There's a lot of relationship between, I think, statistical physics and this type of problem, because in statistical physics, you have to do all this important sampling to get in through phase space, and it's not clear to me how, when we look at these learning surrogates, which are defined over a phase space, how we make certain that we cover the whole phase space. And I don't think you can, in fact. And so we're going to find cases with points needed which are not in a part of phase space we studied. So those are going to hopefully be flagged. Not in the phase space, not ergodic. We need to do some work there. And that's, as far as I know, there's nothing like that being done at the moment. Actually, even in the industry, NLOGOG, which must also have parts of phase space which they don't cover in their training data. If we come now to hardware, well, we need to, I mean, in my opinion, we're not doing the best job we could on actually designing hardware for the big data HPC convergence, partly because I think people are still sitting in two camps. They should be sitting in one camp. And we better take the best. Unfortunately, we probably will have to take the best of cloud computing, because the cloud computing camp is this big and HPC is that big. And so we can't actually assert too much. Only if we can only assert things that they're absolutely essential to get good performance. If they're just essential to accommodate the history of HPC, then they're not going to survive. So we need to look at everything that HPC does and see what's essential and what's history. So if we now want to do HPCforML, which is what we studied, well, we certainly need to have good communication, because we're going to do parallel machine learning, and those are parallel algorithms are at least as hard as the ones in simulations, things like latent Dirichlet allocation and graph computations, both of which were done at this HPDC conference. Those are very challenging parallel algorithms, comparable in difficulty to the difficult simulation algorithms. And so we have, like graph algorithms, have high synchronization overheads. LDA can be very load imbalanced. We do not know when deep learning will be suitable for GPUs, because some papers claim that actually CPUs are better for the recurrent neural nets, which are the variant of deep learning we're using in time series. And of course, we know that GPUs are better than CPUs. So all of these issues need to be borne in mind in HPCforML. And we are going to need fast local disks and accelerators, the GPUs and FPGAs and so on. And we always will need, I think all machines need high-speed networks. Unless, of course, we're only doing pleasingly parallel problems when we can get away with much lower speed networks. But the leading edge applications, I think, will always need high-speed networks for both the HPCforML and MLforHPC. So this slide here compares big data and simulation applications. We have here in purple types of machines. We have two axes: synchronization, from loosely synchronized, very loosely coupled, to tightly coupled. And the amount of disk I/O. These are two characteristics of relevance here, in that maybe the dominant industry application, which is on commodity clouds, using pleasingly parallel or MapReduce, which are not very strong in synchronization constraints. And this is probably the current largest big data category in terms of number of jobs. And the difference from it and, say, classic MPI jobs is the reason why often people think big data is different from simulation, because simulation sort of is, at least in terms of publicity, often over here in the tightly coupled, although there's lots of important relatively pleasingly parallel parameter sweep jobs for simulations over here. Then we have commodity clouds. We have HPC clouds, which we discussed the architecture, and also the supercomputers, where we have high performance interconnects here to do parallelism. And we also have a lot of very irregular problems like graphs and LDA are sensitive to memory access. And in that sense, they're very similar to simulations like unstructured, adaptive, sparse PDE solvers and things like that. The ones in the middle here often have linear algebra at their core, and sometimes even full linear algebra, as we see in deep learning. So the purpose of this is to say there are a spectrum of applications for big data, a spectrum of applications for simulations, and they both pose the same challenges. Maybe the only thing that is a little different is that big data often or always has lots of I/O. I mean, if you're running a compute-dominated machine learning code, that's not true. But in general, you'll always have lots of I/O because that machine learning code needed to load some data. But in terms of the difficult parallelism and the need for important interconnect, they actually are pretty similar. And that should be borne in mind in building these systems, that we have to really add in the disk I/O, but the interconnects are going to be to fall into two classes: commodity, person-oriented applications, which will not need strong interconnects actually for any circumstances, and HPC clouds and supercomputers, which will need good interconnects. Okay, that's just to illustrate how we have to design HPC for ML, and now we go on to ML for HPC, which is even more challenging because it has everything. So now coming to ML for HPC and the hardware needed. So we have to do both simulations and data analytics and their integration. And their integration is possibly there are going to be two jobs running, and these jobs will intermix with each other. And we need to support that intertwining of ML and HPC. Dynamic auto-tuning certainly has that. And these time series jobs will also have that feature, where we're going to have to, as a function of time, switch back and forth between machine learning and simulation. And so that says we're going to need machines where we can spread the simulation and machine learning throughout the machine in a sort of homogeneous fashion, which suggests that an architecture where locally you can do either, and if they have different accelerators for machine learning and simulation, that's going to be particularly interesting. We will always need fast communication, but we'll also need fast I/O because we're going to produce lots of data to actually exchange information between these two components, and they have to be sent both between threads on a given node and probably between nodes. And so this will be pretty challenging hardware. I don't think it's exhibited in current systems. Now we have a single slide with conclusions. 4 conclusions. Well, even though HPC is not thriving by standard metrics, it is not disappearing by standard metrics, and it's sitting there okay, because we have these future, which future is exciting. Everybody needs systems, and we just need to align our communities better so we don't get the big industry systems community reinventing all the HPC ideas. So one way we can help this happen is to collaborate with industry, which is the dominant systems people in this field. And an idea I mentioned, a trivial idea, was working with MLperf. MLperf is not trivial, just the idea of working with it is trivial. I mentioned the global AI modeling supercomputer, which is the overall framework we should be developing. That supercomputer must support ML for HPC and HPC for ML. We're going to have, and we also need to link to the edge, training on the cloud, inference, and training on the edge. And the last part of my talk was about ML for HPC and HPDC. It's incredibly promising. We're going to get our zettascale performance before it, at the similar time to people bring up exascale machines. We need to look at the hardware and software for general ML-assisted speed up of computation. And I gave you some exciting examples from an IU where we were doing nano and bio applications where we can actually engineer your health. We're going to do nano devices built using nano simulations, which are ML assisted. And we're going to do bio simulations using digital twins of your disease running around in your tissues. And that's all going to help you be better and happier. So this is HPC for good. Thank you, everybody. And I hope you've enjoyed this talk. I certainly have enjoyed giving it.